All right, welcome to mini lesson number 2. Today we're going to talk about indistinguishable particles. In the last lesson we talked about composite partition functions when we had a bunch of constituents that were in principle distinguishable. So this is still chapter 6, section 6 of Schroeder, and also a little bit of appendix A. So the basic idea is that if you're dealing with most particles in nature, the idea of labeling them, even imagining labeling them, is not physical. And so this thing that we did where we said we've got particles where we can call one the red particle, one the red particle, and one the purple particle, just doesn't make any physical sense. So if these are electrons, even though in PowerPoint you can make one red and one purple, there's no physical experiment you could ever do that would allow you to distinguish between different situations of this labeling, right? And so in particular, these diagrams where we've got purple in the ground state, red in the excited state, and vice versa, are not actually distinct diagrams if the particles are truly indistinguishable, okay? Again, almost all fundamental particles have to be regarded as indistinguishable. Let's not even say almost. All fundamental particles are indistinguishable, so that this coloring or labeling with A and B or whatever is an illegal operation, and you can't do physics with these diagrams. It doesn't mean that what we did last time is not relevant. We'll see at the end how to understand when it is relevant, and we'll also see it in the next mini lesson. But what we're doing now is a different circumstance where this is not allowed. And so what we're saying is that these two diagrams are really equivalent to just one. And so you can't count these two as distinct. There's only one diagram that matters here. Right? One particle in the ground, one particle in the excited. It doesn't matter which is which. There's no experiment you could do that could distinguish a circumstance where you had swapped these two particles for one another. So what does it mean in practice? It means when we compute the composite partition function for a case of two indistinguishable particles in the two-level system, we have one fewer Boltzmann factor to include in the sum. So we still have our 2 in the ground state that gives us e to the 0, which is 1. But now when we have 1 in ground and 1 in excited, we only have one diagram and one Boltzmann factor to count. That'll give us an e to the minus beta epsilon. And then just like in the previous case, having the 2 in the excited state gives us e to the minus 2 beta epsilon. And so we know the exact partition function for this case. It's this expression, 1 plus e to the minus beta epsilon plus e to the minus 2 beta epsilon. So this number, whatever it is, will be smaller than the z2 we got for the distinguishable case. Now in the distinguishable case, we knew that z2 is equal to z1 squared. Do we have a general formula in the indistinguishable case? And the answer is no. We have a specific answer for this, right? This is true for two indistinguishable particles in a two-level system. But we're going to see that we're not going to have a really simple formula for the indistinguishable case. So one thing to say is if you've only got a small number of particles, there's almost nothing you can say. And in fact, maybe you should question whether you should even be doing statistical mechanics, right? You don't really need a partition function if you've only got 2 particles and 2 levels. We just use it because we can draw the diagrams. So let's make a guess. What if we took the distinguishable answer for the composite z, right, namely z1 to the n, and just divided it through by the permutations of the n particles? Right? So just rearrange the number of ways you can rearrange n particles taken n at a time. As it's hopefully obvious that it shouldn't really change much if you rearrange them physically. But the question is this quantitatively correct as a formula? And the answer is, if n is large enough, and there are many more quantum levels than you have particles to put inside the levels, this formula will be very, very accurate. So once again, if n is not very large, then we don't really need to use StatMech. And then the second thing, if you have a large number of particles compared to the number of levels, you actually have to be much more careful about quantum statistics, and that will be the topic for Chapter 7 primarily. So let's just consider some examples of how this goes. Let's consider the limit of infinite temperature when our physical interpretation of Z sub n, this is supposed to be a sub, just counts the number of energy diagrams that you would have to draw to show how the particles are distributed. Right? Because each Boltzmann factor associated with each diagram will give you a contribution of exactly 1. And you just add them all up and it just counts. So for the distinguishable case, Z2 goes to 4. There are 4 diagrams for the 2-level system. For the indistinguishable case, we saw that one of those diagrams was redundant, and so the Z2 gets reduced to 3. If we apply the formula that I just wrote, namely Z1 to the n divided by n factorial, you get 2. And so 2 does not equal 3, so you can see that for a small number of particles and a small number of levels, this formula is actually not very good. So same thing if we had n equals 3 in a 2-level system, Z3 is 2 to the 3rd, which is 8. If it's indistinguishable, you can actually draw those diagrams yourself. Please do that, and you'll see that there are only 4 diagrams. But then the formula that we get gives us 1.33, which actually seems farther off than the case for n equals 2. So that's interesting, and it points out that it's not just a large n that you need. It's a large n and a large number of levels. So in this case, if n equals 3 in a 2-level system, we actually have more particles than we have levels. And so the accuracy of the formula becomes actually worse. We can see in all cases that the formula tends to undercount. And the reason for that is because it assumes that the particles are not occupying the same levels. So we'll see how that works in the next slide. Right? So if we have a large n and a low particle density, dividing by n factorial works. But the whole idea behind n factorial is that it only works perfectly if you assume that no levels contain more than one particle. And so you can see in this diagram on the left-hand side what I mean. If we have a bunch of levels and a bunch of particles, if they're all in different levels, just permuting them changes nothing, and the n factorial precisely corrects for the fact that permutations don't change anything. However, if we imagine putting all 4 particles in the same level, it's true that permuting them doesn't change anything, but it doesn't quite factor out exactly the way the number of diagrams would be counted that have this condition. So the nice thing about this is that for large enough n and large enough numbers of levels compared to n, the diagrams with only single occupancies are by far the majority, right? And so these ones, if you've got a lot of levels, these ones where you've got multiple occupancies per level are relatively few, and so ignoring them doesn't actually change very much in your calculation of the partition function. So let's do an example to show what this means and think about 2 particles occupying 5 levels. Maybe let's not try to draw every possible diagram. You could do it, but it's tedious. So let's just start out and kind of get a feeling for how it's going to go. So we could have double occupancies because we only have 2 particles. That's the most multiple occupancy we could have. It's not Pauli. I'm not talking about Pauli exclusion here. I'm just saying we've only got 2 particles. So there are only 5 possible double occupancies. You can put them both in the lowest You could put them both in the second, the third, the fourth, the fifth. If you count them up, there's only 5 of those diagrams with double occupancies. And so by contrast, there are many more diagrams where you have only single occupancies. Right? So for 2 particles in 5 levels, let's say we choose to put the first particle in the ground state, well then we can draw 4 other diagrams where we choose successively to put the second particle either in this one, this one, this one, or this one. And then for every possible choice of where to put the first particle, there are 5 of those, we'll get 4 diagrams. And so I think there are 20 total diagrams that have only single occupancies. And so that's 4 times as many diagrams with only single occupancies as double. So you can imagine if you now start to think about having Avogadro's number of particles in Avogadro's number of levels times 5, the formula becomes really, really accurate. So this is our breakdown from what we've done in the last 2 mini lessons. We have a formula for the composite partition function when we have distinguishable components, which is just z1 to the n. And then when we have indistinguishable components, we have an approximate formula. I guess I should be careful to say that. This applies to approximately for large n and large numbers of levels, just by dividing through the permutations of all the particles. So how do we know which is the right one to use? I think, so partly it's going to be experience, but the simple answer is everything that's a real fundamental particle that you would find in the periodic table or the CRC handbook or the particle data book is going to be indistinguishable. So electrons, protons, neutrons, any atom, any molecule, crazy particle physics particles like pions, lambdas, muons, quarks, these are all indistinguishable. Real particles in nature, even if they're composite, have to be treated as indistinguishable components for doing statistical mechanics. So by contrast, distinguishable statistical mechanics is going to come about when the components of the system that you're thinking about are more like organizational concepts rather than fundamental building blocks. And so an example of this is the oscillators in an Einstein solid. So these are not actually particles, right? The oscillators in Einstein solid are not the atoms. In some sense, they are the vibrational degrees of freedom associated with the atoms. And so there's no, the way nature works is that thinking about those degrees of freedom is not they are not indistinguishable components. They are actually distinguishable. Conceptually, it's allowed. And so, yeah, the second way to say this, and is actually just another example of the oscillators in the Einstein solid, is that anytime you're dealing with different degrees of freedom, these are just organizational principles. They're not, right? They're like breakdowns of different modes, rather than actual particle constituents. And so the example is, what if you wrote the total energy of a molecule as its translational energy, its rotational energy, and its vibrational energy, right? If you would put these things inside the expression for the canonical partition function, you would do the same analysis that we did in the last mini lesson, and you would come out with the total partition function, including all of these degrees of freedom, would be the product of the partition function for the translations times the partition function for the rotations times the partition function for the vibrations. So again, when the constituents are real particles of matter, they will always be indistinguishable. If they're just organizing principles, in other words, degrees of freedom, you can treat them as distinguishable. And so we'll be doing some examples of both of these in the next 2 mini lectures. So we'll see you next time.